Hello students, welcome. Previously, lesson 2, form 4 topic 3, you are dealing with factors affecting rate of reaction, and we have done example 1, which was concentration of the reactants. So today, lesson 3, we are going to go to the second factor affecting rate of reaction, which is temperature. Okay, we are saying increase in temperature increases the rate of reaction. Reason being, we are told this is because an increase in temperature increases the kinetic energy of the reacting particles, which make the reacting particles move faster, hence collide more frequently with sufficient energy to cause more effective or successive collisions by unit time. Hence, increase in the rate of the reaction. Remember, we have done the collision theory. We said collision theory, we are supposed to consider three things. One of them, we are told the reacting particles must collide. And they have to collide in their correct orientation, and they have to have the minimum amount of energy required to start a chemical reaction, which was activation energy. So we are saying if you increase the temperature, it increases the kinetic energy of the reacting particles, which lead now the reacting particles to collide more frequently by unit time. Okay, next, let's compare the rate of reaction at different temperatures. So we're saying at a high temperature, the reaction is faster, while at low temperature or at lower temperature, the reaction is slow. Why? This is because at high temperature, there is high amount of kinetic energy in the reacting particles, hence increase the number of successive or effective collisions by unit time. While at low temperature, there is less amount of kinetic energy in the reacting particles, hence decrease the number of successive or effective collision by unit time. Let's now see the graphs or the curves for the combination of the rate of reaction at different temperature. So here we have the total mass or the volume of the product, and here we have time from the start of the reaction. The graph that have more steeper, which is this, has high temperature, hence faster rate of reaction. So this one, which is less steeper, is the one that's having low temperature, hence it's having a lower rate of reaction, or rate of reaction is lower. Okay, next we are going to go to the third factor. The third factor affecting rate of reaction, which is surface area, or the size of the particles. So we are saying increase in surface area increases the rate of reaction. Reason? This is because increase in surface area increases the area of contact between the reacting particles, which increase the number of effective or successive collisions by unit time. So we are saying comparing the rate of reaction at different surface area, we are saying reaction is faster when using powder, unlike chips or granules, where rate of reaction occurs slowly. For powdered, there is a greater area of contact, hence high number of effective collision by unit time, unlike granules or chips, in which there is less area of contact, hence few number of effective or successive collisions by unit time. Okay, next we are saying note, usually powder has small particles than granules, and that granules have small particles, are small in particles than lumps, and we are told fillings have small particle size than ribbons. You have to know that. And next we are having two curves to compare the rate of reaction at different surface area. The curve that is steeper, that we are having greater surface area, e.g. powder, so the rate of the reaction is faster. Then the one that's less steeper, here we are having smaller surface area, e.g. lumps or granules, rate of reaction is slower. Okay, we go. The fourth factor that affects the rate of reaction, which is catalyst. So what is a catalyst? A catalyst is a substance which alters the rate of a chemical reaction but remains chemically unchanged at the end of the reaction. So I told a catalyst works by lowering activation energy of the reaction, thus it provides short route for reactions by minimizing energy required for the reaction to proceed. That's the activation energy. It lowers the activation energy. A particular catalyst alters the rate of a certain reactions, but not all the reactions. For example, manganese peroxide will only alter the rate of a reaction for the formation of oxygen gas, which is the composition of hydrogen peroxide. We are told it should be noted that the energy of the reactants and the products remains the same, but the activation energy is lowered. Most catalysts work by providing a surface on which particles can react, since the rate of reaction increases with increase in surface area. Therefore, solid catalysts are more effective when used in powder form rather than in granule form or in lumps. So here we have graphs showing the catalyst. Okay, here we have the energy, and here we are having the reaction path. This is an energy level diagram for an exothermic reaction because the products are having a lower enthalpy content compared to the reactants. So this is an energy level diagram for an exothermic reaction. So here is where we're having the activation energy for the uncatalyzed reaction. But when we use catalyst, the activation energy is lowered. So this is the activation energy for catalyzed reaction. When we use a catalyst, the activation energy is lowered. Because we said a catalyst works by lowering the activation energy for the reactions. Thus, it provides a shorter route for reactions by minimizing activation energy required for the reaction to proceed. So here is where we are having two curves, and these two curves, one of them we are using catalyst, the other one we are using without a catalyst. So here, reaction with catalyst, faster rate of reaction. Here, reaction without a catalyst, the rate of reaction is lower. Next, we are going to go to the fifth factor, effects that affect the rate of the reaction, which is light. We are told light is a form of energy. It influences the rate of some chemical reactions by energizing some of the particles involved. This increases the number of effective collisions, thus increases the rate of the reactions. So we have some examples of the reactions which are photochemical reactions. So we are told the following are some examples of photochemical reactions. Number one, photography. So we are told photographic blades are normally coated with silver bromide. So we are told processing of films is done in a dark room to avoid decomposition of the silver bromide. So number two, part B, we are told reaction between chlorine and hydrogen. So we are told under ordinary temperatures and pressure, chlorine and hydrogen do not react in darkness. However, exposed to direct light, the reaction is explosive. Here we have chlorine gas plus hydrogen gas. Under ultraviolet light, we're having hydrogen chloride gas. So C, which is also a photochemical reaction, is the reaction between bromine and methane. So here we are having bromination of methane does not take place in the darkness, but in the presence of light, the reaction takes place rapidly. So here we're having methane gas plus bromine gas under UV light. We're having bromomethane and also hydrogen bromide gas. So D, we're having photosynthesis. We are told during photosynthesis, carbon dioxide and water are converted into sugar and oxygen, which are useful for plant growth. The reaction is 6 moles of carbon dioxide gas reacting with 6 moles of water, which is liquid. Under UV light, ultraviolet light, we are going to have glucose and also 6 moles of oxygen gas. Then after that, we are going to go to the sixth factor affecting the rate of our reaction, which is the pressure. Pressure has no effect on reactions involving solids or liquids. It only affects reactions in which either the reactants or products are gases. Increase in pressure of reacting gases by compressing brings the gaseous particles closer, thus increasing the rate of effective or successive collisions, hence increases the rate of reaction. So to compare the rate of reactions at different pressures, we are told rate of reaction is faster at high pressures and slow at low pressures. Reason, this is because at high pressure, reacting gas particles occupy a small space, hence increase the number of effective collisions by unit time, while at low pressure, the reacting particles occupy a large space, hence decrease the number of effective collisions by unit time. So here we have two curves showing the comparison of the rate of reactions at different pressures. So the one that's having steeper, that's having a higher pressure, hence faster rate of reactions. The ones that's having lower pressure is the one that's having now, its rate of reaction is lower. That is the end of our video.